Hello, Lab 9, Tuesday. So let's get started with the share screen. Okay, let's do this one first. So here's the order. So it goes, there's these first three are for problem 1, cubic polydiff, polydiff, polydiff M. And then these last two are for problem 2, so 2.1 and then 2.2. And they kind of build on each other. What I want to do is first go through the skeleton code, and then for the solutions, I won't actually be like polling people on what's like the trickiest, because I mean, what I'm going to do instead is I'm going to show these first two first, like 1.1, 1.2, and I'm also going to show linear regression, meaning like I'm going to show like the basic parts, the solutions to those, and then I'm going to leave the polydiff M and my best regression to you guys to do. Because like, although those are the trickiest, I feel like doing them first wouldn't really make much logical sense in terms of the problem. And it also encourages you to use your brain a little bit. Does that seem fair to everyone?
Sounds good.
For people who not sure like what I mean by like the scaffolding thing, it'll make sense once we actually go through these problems. Okay, let's start with yeah, I'll like do the solutions as I go through the skeleton code. How about cubic polydiff? So first of all, I want to kind of very quickly show demonstrate what these are trying to do. So first of all, we have some f, f input, and then we're going to have some matrix that turns it into f prime. So it's going to be a cubic polynomial, and which means it's going to have like 4 elements to it. We're going to represent this polynomial as like 1, 2, 3, 4. You can think this is like 1 times nothing, 2 times x, 3 times x squared, 4 times x to the power of 3. So this is a cubic polynomial. We're going to turn this into, well, just doing the derivation really quick, 12, 6, 2, 1. No, hold on. No, this is wrong. This should be moved 1 up. So 4x to the power of 3, that gives us, and so each of these are going to be like times 1 times x squared times x to the power of 3. So I'll just write this out for reference. And what we're trying to do here is, this is going to always be 0. This is going to be 12. 3 times 4 is 12. 2 times 3 is 6. And this is going to be just 2. We want a matrix that turns this, that turns f into our f prime. Now, what's that going to look like? Well, in the general case, and I'm going to kind of kill 2 birds with 1 stone with this. It's going to be a bunch of zeros padded on the left and on the bottom. And then along this like diagonal above the main diagonal, you're going to have like 1, 2, 3. And it's going to go all the way until whatever order polynomial you have. In this case, we have a cubic polynomial. The degree is 3. So it's going to stop at 3. Later on in the problem, you're going to want to do stuff like this. 1, 2, 3. If we have like a higher order, this will go like 4, 5, etc. And then like the rest of these are all zeros. And then I could like, if you want later, I can like demonstrate how exactly this works. But I mean, in the interest of time, let's just keep it like this. This is what the differentiation matrix looks like. It's just a matrix that you've seen. This is like an AX equals B kind of thing that you guys have seen. Here's your differentiation matrix. This is F, and this is F prime. Now, with that knowledge, we can code this. Now, let me show you a way to do this very cleanly. We have 1, 2, 3 as like this kind of diagonal. What we can do is this. We'll make this diag. We want to make a diagonal matrix. Well, let me be clear on the wording here. We're going to create a matrix with 1, 2, 3 on the first diagonal. If we wanted it to be the main diagonal, we could do 0. But since we're doing it the one directly above, we're going to do 1. And like, let me just show you like what that, if you're interested, just go to help diag, and then it'll show you the syntax for that. I'm using this one over here, where Yeah, V is a vector with n components, and then kth diagonal is like that second input. So diag 1, 2, 3. This will be expanded out once we actually. Okay, let me just do the general case. 1, 2, 3. 1:3. So that's the vector 1, 2, 3. And that's going to be this thing down here. And then for df, all we need to do there is cubic d times our f, whatever f we're given. So once again, a vector, so a matrix times a vector equals, this should be a vector as well. So this is like the f prime we were talking about. So what this is doing is, here's f prime, here is our differentiation. This is our f. Diff again. Okay. Kind of sped through that. Let me drop any questions you might have. What questions do people have so far?
Yeah, I just had a question on like the diag part. So like the one, does that tell it to just like shift up one, or like, I guess.
Correct.
Oh, okay.
Yeah. Let me, instead of here, let me clear this in 3, 2, 1. Okay, this is probably the best way to actually demonstrate this. I'm going to do diag 1, 2, 3. No, let's do this 1:3, comma 1, and that's what that does. Let's try -1, and that's like the diagonal below it. 0, you can probably guess, is that. Notice how it like makes a smaller matrix because I only unplugged in 1 until 3, because the diagonal is only 3 long. So that's how diag works. I think that's the cleanest way. There's other ways to do it if you don't want to use the diag function, but this is the one I like to use the most. Okay. Yeah, that's cubic polydiff. We can go back to this if people want. I'm going to go on to polydiff. Okay, it's a little more involved, but not much. Degree polynomial. I'm going to make a deliberate mistake here and have people correct it. I'm going to say this is length of f. Why is this wrong? For the cubic, if we have a cubic polynomial, and then we have like
because of the
1, 2, 3. I heard something. What?
Because like the 1, like the constants, you're gonna have like a plus ax or something like that. Yeah.
Correct. So what do we need to do to this? Add 1 or subtract 1?
Add
1. So this is our cubic, and then we're going to get we're going to have an order 5. Because remember we had like the 1, 2x, 3x squared, 4x to the power of 3. It's 4 long, but it's only order 3. So 4 equals 3 plus 1. In other words, we want the order, so we need to subtract 1. 3 equals 4 minus 1. So in other words, length of f is n. Well, length of f minus 1. So we need to subtract 1 actually. And if we're not sure, we can just try. We can just, yeah, it's minus 1. So differentiation matrix. Let's do what we did before. Diag 1:3, 1. But instead of 3, we're gonna have n. Yeah. If we wanted, we could have done like, if we wanted length of f minus 1, and then we could plug that into this diagonal over here. It would have made the exact same thing. So here's d, and we have our f, and that's going to compute the derivative as before. So this is all this is a generalization of the cubic polydifferentiation function. Now, I won't go too much into this next part. I will say one thing. You might want to make sure you have this in your toolbox. If you want to do like differentiation m times, MATLAB allows you to use this notation. So let's say we have some sort of matrix, like let's say like matrix equals magic 3. So that's some matrix. If you want to multiply it like a number of different times, You can do it the same way you do with numbers. You can do matrix to the power of 3. And then you'll just multiply a bunch of times. That's like saying matrix times matrix, just like that. So that probably will help you for this step. Okay, I'll stop for questions before moving on to my linear regression. Five, 4, 3, 2, 1. Linear regression. Okay. Now for linear regression, we're getting a bunch of points. Now note that the model, by the way, is y equals ax, no b. There's none of this. What that means is we need to start at b equals 0, aka the origin. And then our line's going to go all the way through here. So even if we have like, even if our points are like this, even that may form a straight line through like some y-intercept, we need to start at the origin. So like this will still be like a best fit line. It won't pass through all the points because we need to pass through the origin. So that's just a conceptual thing. So as for like how to do the actual matrix calculations for this, we'll need to find A, and it's kind of like the ax plus b. I'm gonna write this on top, but think of this as like ax equals y. We're just like we're substituting one thing for another, and so all we want to do is, let's see, we're trying to find a. No, wait, let me flip this around actually. So it's kind of like this sort of formulation. You have an x times, this is like your unknown, and we know we're x and we know we're y. So let's see. We're going to want x. This should be x, or would it be y backslash? No, this is yeah. I don't know why I was doubting myself. X backslash y. It's kind of like the a backslash b we did before. So y hat is going to be our estimation. And so now that we have our a, right, we have some best fit line with slope a. So y equals ax, which means we can take an x, let's say our x1, and then we can use that to predict a y hat 1. The hat means an educated guess. It's our prediction. We start from x1, and then we get our y1. So all we need to do is take this a that we've received and then multiply it by x. So that's going to be our y hat, and then, yeah. And then the Rubin squared error, I kind of didn't leave skeleton code for this just because, it's already up here. Square root of 1 over m. So Rubin squared error, by the way, for people who haven't seen this before, is this. Root. Now let's do this in reverse order, actually. I'm going to clear this. Rubin squared error. So we do error, sum, mean, and then root. So the error right here is like your y hat minus y. That's your at each point, how far are you from the actual point? Like here's your predicted line, and then here's the actual. So y, let's see, y hat, and then this is y. That's called the residual. Sum is you take all of them. No, I'm sorry, this isn't sum. This is squared. Root mean squared error. Squared. So we're not summing yet. We're going to square this residual so that we eliminate like the sign. Like we don't care whether it's above or below the predicted line. We're just caring about like the absolute value of that. The mean, we're going to sum all these up, sigma notation, and then divide by the number of points. And then once we're all done with that, we take the square root of all of that. And the reason we take the square root, that's just like a units thing. We're just trying to, what's it called? We want something in like units of y, because otherwise we're squaring this, so we kind of get rid of that. We're getting rid of, like, we're making it in units of y squared. That's kind of like a extra thing. But if you minimize like the non-square rooted one, it shouldn't matter. That still gets you what you want. Okay, I saw something in the chat right now. Yeah. Okay, pause for questions while I'll check the solutions to make sure this is exactly what they want. Whoops. Yeah, I can open this up actually. Yep, okay. See something that's true. Okay, Nicola is gonna continue with that. I'm gonna move on to my best regression. And I'm not gonna do the entire thing, but I'm gonna do the first one just to kind of demonstrate. Clear again, 3, 2, 1. Stop annotating, and then my best regression. Last one. This is a more general version of my linear regression. You should be able to take 3 different like not linear models. So you're going to want, here's your thing up here. And this is what your model denotes. It's basically 3 different models depending on what you plug in: sine, cosine, x squared, x, or e to the power of x and 0. And the way we're going to do this is we're going to write it like this: y equals, let's do the first one as a demonstration. So y equals sine of x, a sine of x, plus b cosine of x, plus c. And then what that looks like in matrix notation is this. Here's y being some vector, however many y's you have. We want sine of x, cosine of x, 1. And this is going to be a, b, and c. So I just kind of pulled out the unknowns, a, b, and c. Now this matrix right over here, I want to store as whatever corresponds to this particular model. It's like, what is our a, basically? I'm going to want the first column to be sine of x. Note that x is a vector, by the way. So this is going to create like sine of x1, sine of x2, sine of x3. So it's going to be a column vector. Sine of x. I'm going to do the same thing with cosine of x. Be careful. Don't do 1 for this last one, because all these need to be the exact same size. Visually, this is what we want. Sine of x1. I'm going to do 3 x points for clarity. Sine of x1, sine of x2, sine of x3. Same thing for cosine. This should be a 1. Now, because we need to match the size, we need this to be a column vector of 1s. So in order to do that, we can't have 1. What we want is, there's a few ways to do this. Let's do 1s. Length of x, comma 1. I'll clear that in 3, 2. Let's just kind of clear this part. Okay. That's our matrix. And if we want the coefficients, that is our a, b, and c, we'll simply do a backslash operation, matrix backslash 1. Can someone tell me what our prediction will be? What's going to be our y hat? How do we get that? Remember the procedure we did for our linear regression.
Are you talking about like when we do like the backslash thing, like the whatever?
We already did the backslash. That's our
okay.
coefficients. What we want is like here's a hint if we go back to that. kind of like we have our coefficient times our whatever our x is.
The first coefficient times sine x plus the second coefficient times cosine x plus the third coefficient.
It'll be, let's see. Yeah, so the way we do that would be like matrix times coefficient colon comma 1. Let me see that that's right. Yeah. So I believe this is right. Yeah. Okay. And one thing we could do is, did I miss anything? I don't think I did. So that's the first one, by the way. That's how. Yeah, I'll leave this as, I'll leave this at the type 1. You guys do type 2 and type 3, and then same thing for polydiff. But I've shown the code for this one, and the first one. So that's going to be a skeleton code plus a few solutions to lab 9, and I'll open this up to questions. Lab 6 feedback or anything else. I heard that there's a quiz this week that was like 2 questions long, and they're like super easy questions.
Dennis, actually, do you know where the reports are?
For like the feedback? Or you mean
Yeah, the feedback.
Oh, so what I usually do is I go to assignments, lab 6, and then view uploads. And then I can just control F, and then like the files that are like updated by the reader with like the feedback and all that are downloadable.
Oh, sure.
Yeah,
Because
need
they
help
were
with that.
sending them before, but they kind of stopped doing that.
Oh, someone wanted me to scroll down to the last code. For the very last one, you're talking about my best regression, right? I think. Oh, I see. There's nothing. Yeah, there's literally just an end statement. Yeah. Okay. Let's stop the recording then.